Hey everyone, it's Dr. Calkins again with our last installment of Week 5, Chapter 5. When it comes to bond polarity, we're just going to deal with that in Chapter 6 because it ties together pretty well. So as far as nomenclature goes, we need to deal with ternary. And if you're ternary, it's because you end in ATE. A fun way to learn this is T43. And this is on page 192 of Supplemental 5 of your lab book. Is what I'm drawing in. We skipped this in an earlier lecture because I knew it was coming up for this one. So T43 is just a fun way on the internet to learn the AT ions that are big and scary without much effort. So we're going to draw first the T box. It looks like the letter T on the periodic table. Underneath it looks like the number 4. We're going to trace it as well. And then we have 3 boxes left. That means everything else is not too useful. It's just part of the periodic table that we're not worried about. So we have the T box, the 4 box, and then the 3 box. What we're going to do next is fill in exactly what the periodic table looks like. So we could do the exact same thing on this one. Draw in the T box. Draw in the 4 box. And then draw in the 3 box. So when we do that, really what we're doing is adding 3 oxygens, which is the first letter of 3, is the letter T, to that entire section. And then as we do that for the 4 box, you could probably expect if there's 3 oxygens in the T box, the 4 box would characteristically have 4 oxygens. No coincidence, but we'll take it. And then the 3 box, just like it has 3 boxes, also has 3 oxygens. What's nice about this is all of these will end in ATE, not IDE. So not like what we saw earlier in the video, separate video with binary compounds that are all ternary. Then we have to deal with charges. Well, remember that by themselves, these were negative 1s. Even with 3 oxygens, they're still negative 1s. Coincidence, but we'll take it. Even with 4 O's, this family is still a negative 2 with or without the O's. That's true, so coincidence, we'll take it. Phosphate and arsenic family is a negative 3 by themselves, but even with 4 O's, still a negative 3. So huge coincidence, but that gives us most of the answers with or without the oxygens, which is nice. So the number boxes fit perfectly to the IDEs as far as charge goes. Predictable for 3 based on the number of oxygens they have in the AT compound, but up here it's different. Just do this one more time. Negative 3, negative 2, negative 1. So it descends negative 3, negative 2, negative 1 across both the T box and the 4 and 3 boxes. And that's the 8s. So this would be borate, carbonate, nitrate, silicate, phosphate, sulfate, arsenate, selenate, telerate, chlorate, bromate, and iodate. The fastest way to learn these without flipping out another dozen or so flashcards. So now it's just using these with names. So as we use these with names, think about how they go together. So as we do that, let's just look at this T box first. Think about if we had a sodium and now a carbonate. Group 1 plus 1, cross the 1, cross the 2, so we get Na2 CO3. So we're still crossing charges just like before. But now instead of sodium carbide, we would say sodium carbonate. So AT ending because we have some magic number of oxygens determined by T43. However, if we were to take something like iron and a phosphate, phosphate is predictable, it's in the 4 box. So try to get both of these in the same screen. Let's go up a little bit maybe. So iron, the problem we have here is it could have multiple charges. Let's just say it is a +2 to make it tougher. If these are different, we have to still cross them, but we don't want 42 oxygens. So we can't say Fe3 PO42. We would say PO4 twice. So we need parentheses when that happens. So you still cross charges even though they're scarier. And when we say this, we could say iron, in this case 2, because of its charge of 2, And then instead of saying phosphide, because that would be binary, this has got 3 elements, that's ternary, we would say phosphate. But because iron has a 2 and a 3 charge, you may see ferrous phosphate, because that's a lower charge. So worry about those ideas, high and low, 2 and 3, but also worry about which kind of box did it come from, the T, the 4, or the 3 box. One step further from this idea is if you have T4-3, so we'll kind of have the shadow of it underneath us. If you're in this T4 and 3 kind of idea, if you lose oxygen, you were an 8, that's the whole T4-3 idea, you would become an ite. So if you pick any ion over here like PO4 -3, if you lose oxygen, you're going to become PO3 -3. So this would have been phosphate, and now this is going to be phosphite. You can do that for just about all of them. So losing oxygen changes you to an ite. It's also true though that if you were to take chlorate, ClO3, it's in the 3 box, not the 4 box. Chlorate, you can lose oxygen, become chlorite, just in the same way as above. But you can also lose oxygen again and become ClO -1, and now you're hypochlorite. So you're still ite because you still lost, but we add hypo when you lose more than 1. In this case 2 oxygens total. So notice we lost 2 oxygens, and that's why we're still an ite, because we're losing oxygens, but hypo now because we've lost more than once. It's also true that you can gain oxygen, but because you're gaining oxygen, what's nice is when you become ClO4 -1, you're still an 8, so you're still chlorate. So 8 still an 8, because we still have a high number of oxygens, but because now we've added an oxygen, we've gained an oxygen, we would say now perchlorate. So you have that per when you go in the opposite direction. And you really only do this for the halogens. So perbromates, peridates, hypobromites, those kinds of things are based on the number of oxygens. So it's really about looking at the number of oxygens, seeing how it fits with T4-3 first, and then applying to it. So as we name things in this with acids, we have something even more unique to worry about. So let's talk about that, and then we'll be done with this portion. So with acids, ternary acids in particular, we have this pattern of T4-3. So T4-3 is our clue. It's going to be an ATE. We now know that if we're losing oxygens, it goes to an ITE. If we lose more, it goes to a hypo-ITE. If we gain, it goes to a per, but still ATE because we're still a higher number. So the clue still is, where did you start? And what's unique about ternary acids is when you change them to an acid by adding H+, do this to all of them. Just remember the perates and the hypoites really only for halogen-based ternary polyatomic ions. When you do that, you're going to go to ic for an 8 and os for an ite, and those are acids. So icanose is used again not only for transition metals but for compounds like these. Just be aware that if you were a perate, you're still going to keep per, and you're still going to keep hypo. So those are along for the ride. If they're there before, they're going to stay there after. But it's still ite versus a, ic versus os. A fun way to remember these is if you came from an 8 ion, even if it's a perate ion, you could remember something like I8 something icky. So 8 ions give you icky acids, basically. So 8 goes to ic. For this one over here, you could help remember it with Sprite is delicious. So ites go to os acids, and that can help you remember those given a multiple choice true-false kind of question. So if I were to give you something like HClO2, how would we name it? Well, again, this is a ternary acid because it has hydrogen, and then it has some other more than one atom kind of partner, anion in this case. So because it's not HCl, it's not hydrochloric acid, that was a different lecture. That's binary, this is ternary. So it doesn't come from something that ends in IDE. We need to know, where does it belong in this chart? Well, if what we saw earlier was chloride is in that 3 box with 3 oxygens, this is 2. So if chlorate was up here with 3, this must be chlorite with 2, so we just followed across and this would be chlorous acid. We could also call it hydrogen chlorite if it weren't an acid and it's not in water. But notice that ite gives you that ose acid. If I were to give you something like H2PO3, same kind of idea. This would be H3 to be correct. So what's important over here is we have 3 oxygens. How does it relate to T43? Let's look for phosphorus. Phosphorus happened to be in the 4 box. So if the 4 box is now PO4, PO3 must have dropped down. So this too would be phosphorous acid because it came from hydrogen ions, in this case 3 of them, and the phosphite ion. So I gives you O's once again. If we wanted phosphoric acid, we'd need H3PO4 because then it's the T43 ion specifically. We can go over to a Nick acid. That would be phosphoric acid. So you have to be mindful, especially if they throw you a transition metal as well. Then it's not an acid, but you still have to deal with this ate versus ite idea. But it's all about the oxygens. If you can pay attention to the oxygens, you can survive the hardest part of this chapter. Lots of practice in lab coming up, and lots of practice in homework. And that'll wrap up week 5, chapter 5.